Hi, all people in video land, wherever the camera is. I don't know. Hopefully there's somebody there. So I'm going to be talking today about, at the Media Lab, the work I was doing, just to give you a historical perspective, was smart spaces, trying to understand people in spaces, usually with cameras, sometimes with microphones. And this work, in some ways, carries that on in just opening the boundaries up and trying to think about building scale projects. So how do people use buildings? How do they move around in buildings? What are the patterns? What can we learn from those patterns? What can we do with them? And since it's really, from personal experience, it's really difficult to build camera networks that cover an entire building. It's just an engineering nightmare. And it's not terribly good from sort of a privacy perspective. People don't like to live under ubiquitous cameras. So we moved to sort of sensor networks. And so I'll explain what that means. Sensor networks is kind of a buzzword these days, but I have a particular kind of network in mind, and I'll talk about that. This talk is actually going to be about a sort of the umbrella project. There's a lot of little sub-projects, but that's why there's so many names here, because there's a lot of people, a lot of smart people contributing to the work that I'm going to show. Many of them interns, some outside people, like Carson is at University of Tokyo, and then many people at MERL. Yuri is doing a lot of the analysis kind of work and the interface work. Darren and Jonathan are really helping out on the hardware side of things. So buildings. So buildings are dumb right now, most of them. I mean, it's a nice time to be alive because buildings are starting to become more interactive, more aware. But currently, they're pretty dumb. So the question is, how do we make them smarter? And I'm just going to start up with a really sort of warm-up example. So when we renovated a space a couple years ago at MERL, the building codes required us to put in these little sensors. And this is just a motion sensor. And the only purpose of this motion sensor is to turn the lights off when you're not there. So it's an energy-saving thing. It's now mandated by building codes, at least where we are. And within a week or two, everybody had them disabled. There was a mail that went around and told you how to climb up and tweak the little knobs so that they would basically stop doing what they did. And that's because they were incredibly annoying. And so the question is why? Why are they annoying? And everybody knows why. If you happen to have been in a building where there's a motion-activated light in the bathroom or whatever, everybody knows that story. So what happens is you have one sensor in the office, and you get some readings over time, and then the readings stop. And now the system has to make a decision. The system has to decide, well, are they there or not? So I have the light on. Maybe I leave the light on for a while, waiting for them to move again. Then I turn it off. And that's what I'm supposed to do. I'm supposed to turn the light off. And so, I was talking on the phone, or I was reading, sitting still, light goes off, waving my hands, it's really annoying. So that's why everybody disabled them. So the core message, I think, in this talk is this problem. And so the question is, if we just had two sensors, if we had a sensor in the office and a sensor out in the hallway, for example, then you see this kind of trace where you see motion in the office, and then this motion stops, and you see motion start out in the hallway. Then you can start doing some real reasoning and say, well, I'm pretty sure I just saw the guy leave, right? Because if you leave someplace, you have to move. So I should be looking for that motion, and I should be understanding it. And similarly, if I see motion in the office, if I never see you outside the hallway, then you must not have left. And so I should leave the light on. Now, that's really simple. And that's sort of the simplest version of what I'm going to be talking about. But that's the gist of it. That's one takeaway message, that's the idea. So the context, it's basically about context. So why am I doing this? So I work for Mitsubishi Electric Research Laboratories, and Mitsubishi Electric makes first order anything that has electricity in it. So there's a lot of opportunities to try to connect. These are all things we're thinking about. I mean, there's a lot of groups thinking about elder care, Georgia Tech and CMU and some people at MIT, in the home, essentially. Some people thinking about nursing homes. And we're thinking about that too. But there's also a sort of a security business that we're involved in. We make basically everything all building infrastructure, heating, lighting, security, access control, things like that. So there's all sorts of systems that could leverage better context. If they could understand how people were using the buildings, they could be more efficient, more useful, more reliable, more informative, depending. So this is just my little laundry list of, what I force myself to think about occasionally to make sure that I'm connecting, to motivate the work and make sure it's going in a direction that makes sense. So Sensor network. So I told you, I promised you to talk about what I meant about a sensor network. So there are a whole lot of smart people thinking about the network part of sensor networks. How do you do distributed algorithms? How do you load balance? How do you mesh network in a way that's energy efficient? All this stuff. I'm not thinking about that. There are lots of smart people thinking about that. I'm really thinking about the sensor side. What do you do if you have a sensor that's the size of a building? What does that feel like? How do you use it? And so the network part really for me is just about getting the data back to some place where I can touch it and look at it. So it's really about the sensors. So the sensors we have in the building right now, we've sort of done a phased deployment. And we started with these, this very smart fellow, Emmanuel, who I think, I'm not sure if he has a job now or not. I think he's looking for a job, so you might want to look at him. He worked with the House End project. Stephen and Tilly, for those people who know, is part of that project as well. And so this is a system based on the MITE board. So this is the MITE. It's a radio processor board that they use in their projects. And he was an intern at MERL a couple summers ago. And he helped us put together this motion MITE. So it's an off-the-shelf motion sensor, same motion sensor you'd find in any motion-activated light or appliance you'd buy. So these are really cheap, reliable, well-understood things. And we hooked it up to their board so that we could get wireless communication. And we installed a whole lot of them. So MERL is now covered with sensors. I say second implementation because a lot of this work is informed by a small camera network that we put up and collected data from. So roughly 20 cameras in a small part of the building. But this was the real target, having some sort of low-cost, easily installable system. And the next generation of stuff we're thinking about and the next generation of installations is this sort of board that we, Darren and Jonathan at MERL designed, which is it's 802.15.4, so it uses standard radio, a standards-based MAC. It does reliable communication. It can do all these wonderful things that Jonathan has managed to make it do. And it runs out of battery for a long time. So for a research prototype, this is key. We can lower our installation costs to nearly nothing. They come in a box with a magnet. We literally just stick them up on the ceiling, and then we just let them go. And they'll run for long enough that we can do our experiments. So this is a little wonder of technology. And the amazing thing about, I mean, if you haven't been, I suppose this is a very much a, that's okay. Come sit down. If you guys are mostly software people, you might not be paying attention. I don't know. But this device, you can order the parts, send them off to a prototype place, have a couple hundred built for practically nothing. I mean, it used to be you had to make your own circuit boards by etching them, and that's just not the case anymore. So the cost on these things is coming down, surprisingly, to me anyway. And you just need a person like Jonathan who knows what he's doing, and then he can make these things. And it's a lot of fun, actually.
What's the communication range?
Communication range. It's 802.15.4 is 2.4 gigahertz, so it behaves somewhat like 802.11b. You can, in the sense of what it penetrates, so you get a sense for that. And the range is maybe not quite as much as 802.11b. It's lower power. It's lower bandwidth, though. It's only 256 kilobits. So, in a space you could probably, since this is very open, I bet you could put a receiver in the middle and get the whole room. But when you get into walls, you have to worry about plaster sort of absorbs it, so you have to worry about the structure of the walls. At MERL, I'll show you a map in a second. At MERL, we have about, I think, 7 of the old style receivers covering about 3,000 square meters. And these are supposed to be a little bit better on the range. This also has this chip right here is the radio chip. It implements the MAC. It does AES encryption. It's just crazy. This whole thing draws, the reason we can get 3 years is because this whole thing, while it's sensing, draws about 50 microamps. So that's running the sensor, doing some signal processing on the microprocessor, sleeping. And then when it wakes up, it wakes the radio up for a couple milliseconds, sends a packet, goes back to sleep. So the duty cycle is really low on the radio. So why simple sensors? I'm going to occasionally box out little TRs. You can get these on the MERL website. They usually are other publications, but just to save space, I just mark out the TR so you can go get them. So why simple sensors? So there's a sort of a subversive aspect to this work, which is if you read the literature about this kind of stuff, typically what you see are people doing camera networks, because that's what they know. A lot of the people coming into this field, like me, have a vision background. Those are the sensors they know. There's this desire not to throw information away. So you collect as much information as possible. You reason about it. You get some nice results. Fantastic. And I certainly started that way. But what I realized was that the price of cameras is dropping drastically. And the willingness to spend money on surveillance is rocketing up drastically. And pretty soon these two things are going to cross. And it's become perfectly reasonable, for some definition of reasonable, to slap cameras up everywhere. And you can certainly do some really cool stuff that way. The question is whether you want to. So the subversive aspect of this work is to try to create a knowledge base that says you can do a lot of the things that you can justify wanting to do, like better heating, more efficient whatever, better elevators, even security applications. You can do by having a dense network of really simple sensors and maybe a sparse network of other kinds of sensors, RFID or whatever. And the idea is to economically undercut that future of cameras everywhere. So we did some actually, that's sort of my hand-wavy explanation. Carson Reynolds is a fantastic writer and a fantastic thinker about ethical issues. He worked with Rosalind Picard on effective computing, so he was thinking about the ethics of effective computing. This is this idea that your computer is going to sense your emotional state. Well, that's the wrong word, but in a 2-second presentation, I'll use that one. So you can imagine there are some ethical issues there. And Carson did his doctoral work thinking about those issues. So I leveraged that work, and we got him to help us think about this work. And so his tool is called dimensional metaethics, and I'll I'll undersell the work by calling it sort of ethics an engineer could love. It's sort of you take derivatives in ethical space and think about how systems change as their context changes, and you do it in a very dimension by dimension way. So it was a nice way to think about this, and I'll sort of walk you through this real quick. But there's basically what this slide says is that there's economic reasons to use the sensors, but that's not it. There's also an ethical reason to think about using these sensors. And it comes down to cameras basically provide a greater potential for abuse. If I'm collecting video of you and I can index into it, then I can find video that has nothing to do with my original intention of installing the cameras, but could be damaging. So the dimensional metaethics sort of framework, you come up with dimensions along which the system might change. Like, what's the context? Who's controlling the system? What is the system collecting, for example? Motion versus video, say. Who's controlling it? Is it your boss or your spouse or just random people on the street? Who has access to it? Those kinds of things. And so what typically happens in these systems is engineers like us, we think of cool things to do, and we do them. And we're thinking of an ideal environment, a utopia, where everybody's going the same direction, thinking the same things, and cooperating. And often, things like this, well, it doesn't make such a big deal. Okay, so we collected video. Nobody's going to abuse it. It's okay, fine. But if you sort of shift over to the dystopian world and think about, well, what's the worst possible case, say? If you have cameras, that's actually sort of submissible in court and contains a lot of other sorts of information that wasn't really necessary, that could be damaging. It's very hard to give people feedback. People do these papers where they talk about showing people the video from cameras, but if you have 100 cameras, you're not going to put up 100 monitors. And does it really mean anything? So I think what we came down to, we did this feedback and transparency issue was sort of the central issue, that it was hard for people to understand. If you see an optical glass, there could be video being taken, and you don't know where it's going, because you don't necessarily know the people controlling the building. You don't know whether you should trust them. If you see, so optical glass, I guess. But if you see, where's that picture? If you see this sort of dome, the infrared motion sensors look through this sort of fogged plastic. I think people are savvy enough to know, even just everybody on the street, every man, is savvy enough to know that that's not a camera. You can't see through that. We're used to seeing eyes, and we know what clear means. We know what video is. And so you can immediately know that there's immediate feedback that says, I'm not going to be able to tell that you're picking your nose through that device. It's just not going to happen. I can't tell that you're naked through that device. That's why people put these kinds of things in bathrooms when they want to have motion-activated lights in their bathrooms, because people know that you're not going to see anything through that. So that's the sort of immediate feedback, the sort of transparency that we're looking for, that people can feel comfortable living under these because they know there's an upper bound on what they're going to lose by being viewed. And this was a survey we did on the web, actually. Welcome to 2006, whatever. We published it on Craigslist and did a web-based survey. And so this is not quite scientific, but we got an overwhelming preference. What we were asking people was, well, if we were going to have this this kind of system that would help you, make your workplace more efficient, would you rather it be cameras or motion detectors? Well, okay, sort of looking under the light post. But what we were trying to measure here was whether the everyman was sophisticated enough to understand this difference. And this is some indication as a preliminary study that they are. So that's good. So that's the why. That's sort of 2 takes on the why. So let me talk just real quick about the how. How did we build it? And this is research prototypes. We're working with the company to try to think about what the real thing would look like. But this is what we came up with for gathering data for research purposes. And I've never built anything, like I'm a software guy, I'm a computer vision guy as introduced. I've never built anything on the scale of 500 things. So it was a real treat for me to do this. So these things were the boxes. So you have to think about this, like what's the enclosure going to look like? What kind of, oh my gosh, 11:25 already. You have to think about this. It's a hard problem. You're going to drill holes in plastic. That's really expensive. So we actually printed these. Hopefully I have the video. If you guys don't have a rapid prototype or haven't played with one, it's a lot of fun. So this is a little thing. It prints plastic, essentially. And so we print these things up. And this actually ends up being cheaper than injection molding if you're in the 500 range. You have to get up to because you have to make the molds, you have to get to thousands before injection molding makes sense. So we printed these all, and then you have to get them up on the ceiling somehow. So I actually learned how to use these stilts to put them up. So why? So if you can imagine moving a ladder and climbing up it 500 times, that's why. So this is what they look like on the ceiling. That's me just installing it on the ceiling. So this is what you get. In fact, let me jump over to the live version of that. No? So this is just a little data viewer. When I'm at home, I just show I show people walking around the space, but you get a movie. And all demos are better in fast forwards. This is obviously, time's ticking away very fast here. But what you're seeing is this is a map of MERL. If you've ever been to MERL, the elevators are here, reception lobby, kitchen, seminar room. I'm giving a talk. I happen to be giving a talk about this exact stuff. People's offices are around the outside. So what you're seeing is people walking around the hallways and the lobbies and the meeting rooms and stuff like that. And what happened now is at 12:53, there was a fire alarm. So this is what evacuation looks like. People are flowing out of the meeting room, down the stairs, and leaving the building. So this is the kind of thing that I really wanted to get to. This is like peel off the roof of MERL and look down in it and see where everybody is. It's a kind of view that's very difficult to create from a camera network. Unless you have very dense cameras. This is my boss doing a sweep to make sure everybody's left the building. And then there's one person who gets left behind in the bathroom. They come out in a second. And then it jumps forward in time, and we see people coming up the elevator, going to the kitchen. And we see people come up the fire stairs because they didn't want to wait for the elevator. And you can sort of see people reflow back into this space. So this is exactly what we're trying to get at. We're trying to understand how do people use buildings? What are the patterns? What can we get? So that gives you a sense of the data. So let me jump out from this. OK. So how do you use a sensor network? OK, so then the question is, well, we got the data. We've been collecting data for about 10 months. And we got those sort of phases. So from the 8th floor, we have about 10 months of data. And so the question is, well, how do you get stuff out of that? And at this point, I may run out of time, actually. There's 2 parts. There's sort of 2 takes on this that there's many takes on it. There's 2 takes that I'm attached to. I'm trying to cut one of these out of the talk, like it's like killing puppies. Like I can't do it. So I'm going to try to talk about both. But I'm going to talk about this one first. And hopefully we'll get to that one. I guess there's an hour and then a break and then maybe another half an hour. So this stuff relates to the really interesting demos I want to show. So I want to try to go through this at a very high level, and then hopefully leave time for talk about this and show the demos. Well, we'll definitely show the demos. Hopefully I'll talk about this. But the schism is, do I think about things in a building way? Am I really interested in thinking about the building understanding itself? Or am I really interested in people? And there's different applications. This kind of stuff is for, how do I tune the heating system? How do I predict elevators? Things like that. How do I understand the structure of behavior in the building? And then this one is really about people. It's really, if I care about people, because I'm doing surveillance or security, or I want to do really careful census for disaster recovery, things like that, then I have to sort of think about things in this way. And I'll explain what those mean, what those two things are. So we're going to start there. So this is actually work that I did with Emmanuel, and we published it at this location, Context Awareness. Hopefully we're going to publish it somewhere else, but this is the current publication. And the idea is, I said I wasn't really thinking about the distributed processing part. So we tried to make a nod to it here in the sense that we're trying to find things that are local. So we can build local detectors that only use local information. Because in sensor networks, there's this idea that you want information to travel locally so you can save on communication costs. So you want to aggregate information locally, abstract it, and then only send a small amount of information upstream, because that saves energy. So although we're not thinking about that very carefully, we're certainly thinking about it a little bit in the way we're designing our algorithms for the building. And the other reason to think about locality is that hopefully you want to be able to build relocatable things. You don't want to have to customize the network to every building. So every building has junctions in the hallways or corners or meeting rooms. And you want to be able to build models that can be reused. There shouldn't be, we're all people. There are probably some differences in the way you guys use hallways and I use hallways, but I bet they're really subtle. We're probably very similar. Meeting rooms, things like that. So I should be able to learn models here and pick them up and put them over there. And of course, there's domains. Picking up models that I learn here and putting them in an industrial setting, maybe not so good. But the assertion is that there's a small number of local models that we want to learn. So we build this hierarchy. And this is sort of, there's this work by Aaron Bobek a number of years ago about gesture, hand gesture. And he was thinking about, well, what are the different kinds of models we need to use? What kind of information do we get out of them? How do we think about gesture? If I have a kind of gesture I want to recognize, can I go to some list and say, well, it's this kind of gesture, therefore I need these kinds of models, and this is the kind of information processing. So we're going to try to do the same kind of thing. So we build this hierarchy. And the movement, activity, action comes from, those words come from Aaron. But we're going to reuse it in the sort of building context. So motion is the bottom. There's no context. It's just one sensor. Is there motion under the sensor? Not a whole lot you can get from that. But this is going to be our hardware sensors. And then as we go up, we're going to get more context. We're going to get more spatial context in the sense that we're going to look at clusters of sensors. And we're going to add in other sorts of information. So for movement, we're going to think about no temporal information. We're going to build straight-up detectors, static detectors. And obviously, we're looking at temporal sequences of data, but we're not going to model the temporal sequences. We're just going to model whether things are there or not. And then as we move up, we're going to add in temporal structure. So these are more harder models to evaluate, so things like maybe Markov models. But since we're abstracted up, we're going to have less input data. We're going to have higher level data to think about. And then at the top is this sort of action is the idea of having the context. Walking down the hallway to a certain place is an activity, but going to get your mail is an action. You need to know that that's the mail room. So it has special meaning. It has some link into the context. So this is a sort of hierarchy. I'm going to try to break the work up that way. So the motion is, we've implemented it in hardware. Very simple. I've already talked about that. So these numbers are all old, actually. I should update those. So what's a movement? So imagine this is a little chunk of hallway. So imagine there's a crossing hallway. And these are 5 sensors, one that covers the intersection and some context. So we basically just enumerated all the possible things that can happen in that kind of space. So there can either be no motion, there can be someone loitering at the intersection, there could be someone walking through the intersection, There'd be someone turning corners in various ways. There could be people appearing and disappearing, assuming that there's offices that aren't observed, for example. So this is an indication of somebody, say, coming to a space and disappearing into an office that's not observed. So there's this sort of a set of things that we can expect to see in these kind of chunks of buildings. And we're going to try to learn those. And so we build, we gather data by hand, and we do a boosted, I hope that wasn't 11. OK, we build a boosted set of detectors so that we can detect these, literally they're going to be detectors. We're going to detect these events. We're going to take that activity, the sort of motion at the intersection, say, of a hallway, and abstract it into a higher level label that's something like someone walking through or somebody loitering or whatever. So we're going to reduce the dimensionality and also have higher level labels. So in all the results here, I'm going to show this map. So this is a map of MERL, the 8th floor. So the elevators, which I already sort of talked about. I can't get my little cursor to come up. Anyway, you can read. And this gray area is the part that's actually observed by the sensors. And what I'm going to show is these sort of really abstract map. It's like a sensor map. And so it's just going to be just the sensors. So kind of keep in mind where things are, just to reduce the clutter, essentially. And then dark things are going to generally be high probability, and light things are going to be low probability. So this is showing a particular probability distribution over the space. And so that one happens to be turning. So this is the probability of seeing a turning event at a particular location. And this is really, it's not terribly meaningful, except that just to validate that we're not seeing turning events where they aren't possible. And we do see them where they are possible, and where they're the only option, we see them all the time. So that's good. It makes us feel good about the detectors, that they're doing their job, for example. But that's just to give you a sense of what that display means. So similarly, we can make a straight, walking straight detector. And again, in places where you can't walk straight, you don't see any probability. In other places, this is actually normalized differently. This is normalized by the maximum in the environment rather than per sensor. So what this is really showing you, I like to say this is the first example of a computer being as smart as a building, because a carpet, really. So this is a carpet wear predictor. If you walk into a building that hasn't replaced the carpet in a while, you see where people walk. You see what the high volume pathways are. And that's exactly what this map is. This is showing you where the high volume pathways. So people walk, coming from the kitchen, there it is. Coming from the kitchen, they'll walk this way, which is interesting because they could walk a shorter path this way, except that there are secure doors in the way and they don't like using their card. So this is an indication that people will avoid secure doors in our space. So just to give you a sense of what those maps mean. So as we climb up the, oh yeah, I just pointed at those. These are the secure doors, and there's the coffee. So researchers work down here typically and here, and that's the coffee. So I can show you maps all day, and you can say, oh, they're pretty maps, but it doesn't mean much. So what we did was we presented people with these kinds of maps, and we asked them questions like, where do people stand around in the space? The people at MERL are experts in the space. They walk around it every day. They know how people behave. So we did a survey, and we said, please mark up where you think people stand. And then we generated those probabilities from data. And nobody had seen the generated maps. So that's the survey. This is the map. Nobody had seen these kinds of maps yet. We hadn't done them. So we did the survey first, and then we looked for the data. And so this is just to show you, just to give you a sense that, in fact, it's sane. There's agreement. So people, stand around in meeting rooms, call it loitering or whatever. This is actually a dead sensor. That's why it's white. People stand around the meeting room, the lobbies, things like that. It's interesting to see that people overestimate how much time people spend standing outside of certain people's offices. They're certainly there in the data. And you can see it because you have a Mitsubishi projector, so that's good. Most projectors don't pick that up. So there's some fundamental agreement between the survey and our real data results. So let's climb up the hierarchy a little bit, so I still have time. So the next level, I said we were going to take these detectors and clump them into temporal sequences. So these are models where the temporal sequence is important. It matters that you do a certain thing in a certain way. So the two things we're going to look at in this talk are visits and meetings. So we define a visit as someone coming up to a space, stopping, loitering, and then leaving. So each of those comma-separated things is a movement, a lower level thing. So these are detected symbols that represent some collection of sensor readings. And then similarly, a meeting is going to be either people exiting or entering a space over time. So maybe over 5 minutes. You know how meetings happen. It's scheduled for 10. People show up. Maybe one person shows up a minute, next minute, a couple minutes later, whatever. People aggregating. So this is something where it's important that a sequence of things happens within a certain window of time in a certain way. So let's look at those. So this, again, the survey is on the right, and the meeting is on the left. And so this is detecting meetings, finding places where meetings happen in the space. And you can see there's some disagreement. There's a sort of interesting disagreement about the kitchen. So the survey participants were generally unwilling to call the things that happened in the kitchen meetings. But the system certainly thinks they're meetings. And in fact, we'll see a difference in the next slide, too. One potential error is that elevators look like meetings. And you can see why that is. With this relatively simple model, people are aggregating there and leaving there. So it looks like a meeting place. But you see it looks less like a meeting place than the meeting rooms, which is good. So this is where the disagreement comes between the survey participants. So now you ask, where do people visit? So where do I go and dwell for a short period of time and leave?
How did you train these detectors?
We didn't really. We basically wrote down Markov models to say, I want to see these kinds of symbols in this order. Go. Yeah, I defined, yeah, exactly. So, but the argument is that for portability, I'm basically writing down sentences. I'm saying, in a sense, I'm saying meetings are where people enter. Go look for that. And so it's good that it worked, because that means I can go to a new building and come up with new sentences at a very high level. But you're right, typically you train these models. And so we have to we try to do that. And what's...
The text enter, is that trained or is that...
That's trained, yes.
How's that trained?
We literally put up cameras and annotated data. The reason we didn't annotate the meetings, for example, is even though you feel like you're having meetings all the time, they're rare enough that it was a real pain to go get the data and find it and label it. There's just not enough examples. And it turned out that it worked to just write down the sentence. So we just presuppose the transition probabilities to be some uniform thing, and that works okay. So anyway, this is where the visit thing. So people reported that they were visiting the mailroom and the kitchen, and then certain people's offices, and certainly they do that. But the system really wanted to see the kitchen as a meeting. It really refused to recognize it as a visit. And maybe this is a case where there's some subtleties between those models where if we actually learned it from data, we could pick that apart. Or maybe we need a more complicated notion of a meeting. But remember, these aren't actions. These are not contextualized. It doesn't know that that's a kitchen. So perhaps there's special models for kitchens. So the visit thing, so the action. So this is good. OK, so this is the very simplest action. So this is just to get to the top of the pyramid. I think there's a lot more work here, but I'm going to show one simple thing. And that is that, and again, this was something that we could get ground truth for. So when we send documents to a printer, there's a log that's created, so we know exactly when that happened. And then particularly, people sometimes go pick up their printouts, presumably, if they're printing something. So what we did is we said to the system, here's a sequence. I got a graphic for that. So here's the probability of seeing a visit event in the space based on space, right? And so most people, every day, everybody goes to the mailroom. So that's a highly visited space. It's like the most visited space in MERL. So what we're going to do is we have, what we see here is that each of these little boxes, we have a temporal sequence of visits. At a particular time, there was a visit, and there was a sequence in time. But what we have is this other sequence, right? So we have 155 sequences of visits. And then we have this one sequence of a particular printer's print queue log. And what we want to do is find the conditional probability that this place was visited sometime after this job was sent. That's all we told the system. We said, look for a 10-minute window or something. Go. And what you get is a very different. So this is, just to go back, this is the probability of seeing a visit. This is the conditional probability of seeing a visit conditioned on the print queue. And so what you see here is that you get this huge peak coming out where the true location of the printer is, which is that circle. And you can see that before, in the sort of joint probability, just the probability, you see that that space is a visited space, but not a highly visited space. It only happens sometimes, certainly much less in the mailroom, much less in the meeting rooms. But when we condition it, we get a much different answer. And this, it's hard to tell with a gamma, but that peak is much, much higher than every other peak in the plot. And actually, the other peaks make complete sense. So what do you do after you pick up a printout? Well, you go to the fax machine, you go to the meeting rooms, you go to certain people's offices. That's what these secondary peaks are. And we didn't tell it to pick the first visit, so it's happy to pick other ones. So this is the kind of stuff. So what this says to me, and I was very excited when this happened. We can do it with other printers, obviously. What this says to me is that the pyramid is working to at least some degree. All the little pieces, we've taken the motion activations, we've turned them into movements, we've recognized them as activities, and now we're contextualizing them into actions. And that whole pyramid has to work at least somewhat to get this result. So this is a sort of a validation that that whole structure is working to me. And I was very excited to see this. On the other hand, finding printers is a little silly because you know where they are. but again, just to remind you, we have ground truth for this, so we can get it. And so we're closing that loop. We're doing real experiment here and validating this result. Yeah.
The high probability there is actually determined by the system by looking at somebody printed it and we saw someone have that.
That's right. So given this sequence, we have a temporal sequence of print, not just someone, but many people. I think there were maybe 100 events, 100 print queue events. And so for each of those events, indexes into time, and we look to see if there's a visit at that place nearby. So we're doing sort of a sloppy sort of correlation where we're trying to find things that may have a windowed offset, but we're trying to find correlations there. Co-occurrences. That's right. Yeah. So the next thing I'm going to show you is about how do I show that a person went from here to there. That's a very good point. Thank you. I usually make that point. This part of the system has no idea where you were, where you came from. All it's looking for is that particular location of visit. And it doesn't know that it's, if I printed it, you could go pick it up. That's OK. It'll count that as a hit. You could think about reversing this equation and look for, when I send a job, where do I appear in the space? And I could try to find people's offices. And we thought about doing that. We haven't done it. Does that answer your question? And then there was a question.
Yeah, I was just going to ask if you tried to find people's offices.
Yeah, it's something we thought of. At the time when we did this, we didn't have enough data. And now we do. We just haven't gone back to do the experiment. Because we were doing the other stuff, which I'll talk about in a second. Another printer. Right, so here's the other stuff. So how are we doing on time? Doing OK. Good. All right. I feel like I'm talking super fast. But for the people at home, you can watch the video and probably slow it down somehow. It'll be good. OK, so people-centered models. So that was very space-centered. Just like we just said, the system isn't thinking about tracking people in the space at all. It's only looking at these very localized detectors and trying to build stories about them. In this case, we're building stories about the people, about where could the person possibly have gone. And this part of the work really feeds back into this sort of privacy question, which is, if I'm going to claim that, that these sensors are better than cameras, I have to do two things. I have to prove that they're useful enough to actually supplant the cameras. I also have to push the boundaries hard as possible so I can say, no, this really is the upper bound. I believe this to be an upper bound on the privacy loss. And so this will eventually end in the scary demo, which shows you sort of our furthest push out into like how invasive can it be. So before we were talking about the activations of the sensors and we were building detectors on them. Now what we're going to do is look at spatial temporal sequences of activations. And we're going to say, when people walk through the space, they create this structure, a chain, in the data. And because our sensors are dense, it's relatively easy to do that chaining. Unlike a camera, if you have a camera here and a camera 50 meters away, a lot could have happened. And I have to hypothesize all that. I could have gone this way. I could have gone that way. There could be someone with a similar shirt. It gets messy. But with these sensors, they're only a couple meters apart. So if I see a chain of activations, I can be pretty sure that those chain of activations were caused by the same motivator, the same person, the same car, whatever it is. So what we're going to do is we're going to say, if we see these chains, we're going to pull them out into something called a tracklet. We're going to associate them as a thing, as an object in the database. So this is all database driven. When I show you the demo, my poor laptop was running MySQL with all these chained things in it. It still works. And then we're going to go further. We're going to say, well, at the beginning of a chain, if there's no explanation for that first activation, that person must have entered the space from some unobserved part of the space. So we're going to call that a beginning. And furthermore, if there's an end of the chain which doesn't explain anything, then we're going to call that an end. We're going to put an end on it. And then what we're going to do is we're going to reason in this space. We're going to totally ignore the observations, and we're going to think about these structures. So now it's just a different cut on the data. We're trying to abstract it, again, do dimensionality reduction and abstract out some high-level description of the data that we can reason about quickly. So of course, that's, this is the ideal. Somebody walks out, doesn't get near anybody else, and goes somewhere else. And we know exactly where they went. But of course, the problem with these sensors is that they don't give you very much information. Again, if two people cross paths, I can't tell that I'm wearing green and you're wearing blue. I don't have a camera. So what we do is we put these joins and splits. We say, this is very much classic tracking. Both of these observations explain this one. So we're going to link those together and do a join. And we're just going to take that ambiguity and stuff it in the database. We're not going to try to resolve it. We're just going to keep it around. And similarly, if we see a place where two tracklets can be explained by the same tracklet, we're going to call that a split. So this would explain, for example, if someone comes out of A and someone comes out of B, they meet up in the hallway, they walk for a while, and then they go their separate ways. That's what it looks like in a graph. So this is the sort of the next most complicated graph. And we don't really have any way of knowing that A went to Z or A went to Y. It's ambiguous. We can't tell. Yeah, I should have been clicking those. So in the demo I'm going to show you, just to start getting you warmed up, because the display is, if you don't understand it, you haven't been introduced, you can be a little busy. So I want to give you pieces at a time. So this is a piano roll of data. So there's sensors this way, up and down, and time this way. And whenever a sensor activates, it drops a little blue dot. So you see these structures, right? These are people walking down hallways. And so when we overlay the tracklets on top of them, this is what we get. So what you see here is that here's a start. Where's my pointer? Pointer. Anyway, the little red triangle is a start, and the little white box is an end. And then these are the ambiguous reasons. Even though you can't tell it from the piano roll, these are probably spatially nearby each other, because we have to unroll 2D into 1D. So there's places where we break loops. So this is a case where these two paths were near each other. And you can see there's a lot more complexity than what I had on the screen, because this is trying to record every possible ambiguity. So it gets a little messier than my nice plot. And you can have arbitrary graphs where people, we can do reasoning about, C could not possibly have gone to W or X because this is a directed thing. And these graphs can be arbitrarily complicated. And in fact, as the population of space goes up, they become arbitrarily extended because they just keep going. So one of the scary demo, the sort of surveillance demo, is we decided to try to build a system where a person could interactively disambiguate this graph and say, using their knowledge of the space, their knowledge of people, perhaps other sensor modalities that they have access to, they can disambiguate and pick out a particular graph and help the system to say, well, I know that A went to Y. And so the demo I'm going to show is sort of a graph explorer. And it looks like this. So again, this is the piano roll, the tracklets on it. The red path is the current sort of explored part of the graph, the current subgraph that the person is interactively exploring. And you can see, again, we have the little components, the ambiguities, the begins, the ends, and the tracklets. And then at every instant, the person's job is to disambiguate these kinds of situations. And in order to help them do that, we have sort of a cut on the graph. So this shows your current temporal slice on the graph. And you have things that you've chosen, and then things that you have yet to decide between, accompanied by, in this case, video evidence. And we also give sort of a spatial view in that. So the red path comes up here, and then there's an ambiguity. Either the person goes left or right, and the person has to disambiguate that. So the way to think about this is, one way to think about this is that these sensors provide contextual information that's ambiguous. And you can use that to improve a number of systems, heating systems, whatever. In this case, we're improving a camera system. So we have a limited number of cameras in the space. We're going to try to use the contextual information to make the cameras more powerful. And then the output of this, well, that's just the video evidence. The output of this process, then, is a collection of video evidence and a track of the person through the space. So Yeah, that's a summary. So let's jump to the demo. Let's see here. This takes a little bit to start up. My poor laptop is somewhat unhappy about being made to do this. So there's actually a bunch of really interesting demos. I'm going to try to get in before the end. I want to get in this one. And then I'll go back if people are interested, and I'll do some of the other demos. So you're going to see exactly that display I just sort of walked through. And what I'm going to be able to do is make selections on the space. And I'm going to be able to search in this tracklet space. I'm going to be able to say, show me where tracks started at this particular location, for example, and pull out all those graphs. And then I'm going to be able to walk a graph and show you what's going on. So I've practiced this demo because I have a limited amount of time. Also, the other reason I've practiced this demo is because it's impossible to say to people, well, we just recorded a bunch of data and we're just going to show it to everybody. They don't like that. So what we did is we found instructive examples, and then we went to those people and said, could we please show this particular video? And they kindly agreed. So that's the video you're going to get to see. And what this poor laptop is trying to do is it's running MySQL. This demo is going to come up. It's pulling a bunch of data from MySQL to build the interface. And then as I work on it, it's going to be making SQL queries into MySQL on my poor laptop. So if you ever have the advantage of seeing this demo like on a real computer, it runs much faster. And this should be any second. There we go. OK. Oh, that's just because I touched it. So one of the cool things behind the scenes, I'll just keep talking, is the way that we format these SQL queries. This was one of the many things that Yuri contributed to this project was he really figured out how to craft these SQL queries so that they were efficient and so that they returned ordered lists so you could admit errors and things. And it's very cool. I don't know why it's not starting. I should have started by now. I'm on full power. Oh, dear. So let's give it a few seconds. Maybe it'll come back. There we go. OK. So again, you see this sort of layout of the space with the sensors going off. And now we have these cameras. So we have several cameras. There we go. We have several cameras scattered throughout the space, but not really dense enough to give you a feeling for what's happening in the entire space. So that's where you get this. You see people walking down hallways and stuff. So what I'm going to do, I'm going to pull out a particular person's office. I'm going to say, show me tracks that start at that office. And there they are. So I just did a little query and pulled them out. And I can look at just that list of hits. Let's take that one. And then this is the graph. These are all the graphs. And if I zoom in, we start to see the actual graphs. Like there's a beginning. There's a deterministic graph. Here's the beginning of my hit. This is the one that I just queried. And there it is. So this is the first tracklet. So the person comes out of their office and walks this way, and then passes in front of some cameras. That's what the little white boxes mean. It means there's video evidence of that part of the track. And then they continue on to this part of the space, and they get lost. So let's explore that. I'm going to say explore. I'm going to select that track. And then it shows me the video evidence. Here's the person. Zoom out a little bit. So there's the person, right? Wearing blue. So remember that. And then there's a couple different pieces of video evidence. She walks through that space there. And then we get to this area here, and the system has gotten confused. There's some sort of ambiguity that has happened, and it's given me an orange option and a blue option. And in this case, it's relatively trivial. They're actually, really should have probably been part of the same track. So I picked blue. And now we get to something more interesting. So this is a case where there's a split. So two people cross paths. So what we can do is we look at the video evidence, and it's showing us a different camera. And we say, oh, OK, so this track is the person in the white shirt going to the right. So it must have been the other one, which was the person in the blue shirt going to the left. And there she goes. And then we get, there she is again. So I'm going through this a little too fast, but basically what I'm doing is I'm walking this graph. At every ambiguity, I get a choice. and I get presented with whatever evidence there is. And that could just be the way people are moving on the map. In this case, there's a lot of cameras in this particular space, so I get lots of video evidence. In fact, there she is right there, and I can pick her. There she is. And then I say I'm done. So I walk the graph. And now I can look at, for example, I can zoom back out, and I can see this whole behavior. So I can wipe over it. She comes out of her office, stops at the printer, walks up this way, through there, comes around there, and there she is. So everything before this point, you would never have gotten with the cameras. You wouldn't have known that she stopped at the printer. You wouldn't have known where she came from. And we can just walk through all the video evidence. So this is very much, this is aimed at being a forensic security tool. It says, you don't really have to put cameras everywhere. You can put a few cameras at choke points, and then I can give you the in-betweening information. You don't have to guess. We'll have observations that tell you exactly what happened. And so this is an example of that. And many thanks to Kathy for allowing us to show that in public to everyone. So I'll jump back into this because there's other cool examples, but it's now noon. So let me just quick go back here and just wrap up for the people at home in case they sign off. Go away. So just to say what I said already 5 times, the idea is to create an awareness of what's going on in a building in a way that's economical, both in terms of money and installation cost, but also in terms of sort of privacy cost or human cost. So there's a social sort of pressure to make buildings more efficient or more useful or safer, but there's also a human cost or human desire to have privacy and still want to live in the buildings. And so this is a future we're trying to create. And it projects into lots of the things that Mitsubishi Electric is building: lights, cameras, access control, heating, elevators, all this stuff. So why don't we, I guess maybe the thing to do is to end there and maybe take questions and maybe do some more demos if people are still interested in here. Thank you. Yeah.
So, are there more questions?
Oh, I was supposed to repeat the questions. I totally forgot.
Simple question. I think the motion sensor is very good for privacy because there's very limited information exposed.
Mm-hmm.
In the meantime, this limits its capability of constructing rich context that you may want to construct interesting applications.
Mm-hmm.
So do you have any comments about the capability of the motion sensor system that you can construct?
Right. So that's exactly the trade-off that we're trying to figure out how exactly it balances. So the question is, if you have sort of we'll say justifiable, loaded word, but applications you can justify, like making the elevators better, or making the heating of the building more efficient, or improving the way that you interact with your coworkers to make a more rich space, things like that. Can you accomplish those with these kinds of sensors? That's the question. And you certainly can accomplish those things with cameras. So there's some point at which you have to have enough information. There's sort of a frontier. We have to get above that threshold in order to do certain applications. And the question is, where do these kinds of sensor networks fit? Are they below that threshold? Are they above it? Cameras are certainly way above it, and so that's the question we're trying to answer. And we're actively, and this is active research, we're trying to push all those boundaries to figure out how far can we push them, what can you get, what kind of applications does this enable? And I think there's clear evidence already that if you're trying to predict elevator load, I think you can easily do it with these kinds of things. If you're trying to extract sort of maybe social networks from the space I think there's a spectrum of those. If I want to know who do you talk with in the hallway, I can try to get that indirectly through the graphs by saying, well, I know you tend to interact. There's high probability that you leave your office at the same time as someone else, and you tend to have ambiguous interactions in the hallways with them. Or I could have cameras, and I could see you and them, and I could record that event, right? And so almost certainly you'll get a better data from that kind of thing. The question is, can you get enough data to do what you want with the other kind of sensor? And that's what we're trying to answer. So I don't have answers. If you can go down a laundry list and say, I want to do X, Y, Z, I don't have answers to all of those because we're still working on it. But that's the answer. That's exactly the question I'm trying to get to. Yeah. So. Yes.
So your last movie kind of suggests that there's some space for incorporating some priors or some information about the way
Yes.
that people move in a building. For instance,
Right.
people don't take unnecessarily convoluted paths between
Right.
one person's office and another. So
Right.
I was wondering if you had any thoughts on either incorporating some heuristic or training up some models like that.
Right. So some of the older work I didn't. There's backward and forward-looking answers to that. Backward, we've already done some work, which I didn't talk about today because it's just too much, which was using the sort of less structured approach, treating the sensors as basically a bag of observations and trying to find connections. And that was really motivated by trying to predict, for example, elevator load. So knowing that someone was going to go to the elevator and understanding what's the first part of the sentence that ends, push the elevator button, right? And so that's sort of a version of your question. And we've done some work on that. The forward-looking part is, well, we could probably do a better job if we used some of these structures. And we haven't yet gotten to that with sort of future work. So we sort of touched on it, but I think there's a better answer in the future if we come back to it. Yeah. So I can try to, let me try while I'm answering questions. I tried this yesterday and I didn't have enough focus, but I'll try again. There's a much longer version of this, which is kind of fun to do. So keep asking questions and I'll try to get there if you have questions. Let's see. So this poor guy. So we're going to follow this poor guy. So we're going to explore that. I'm going to select that. OK, so there he is. He's got, this is Bill Yurzunis, a star of Stage and Screen. He's got a white shirt, black pants, and a ponytail, so pay attention to that. And so he starts out a very similar sort of track, heading up into this space. We've got an ambiguity here. Again, it's sort of a trivial one. Well, no, actually, this was some interesting ones. He either turns around and goes back, or he continues on. So we could explore each of those. I happen to know he continues on, so in the interest of time, I'm just going to do that. And so, for example, here's an interesting case where the dense sensors really win. So he comes around the corner and disappears from the camera view. As far as the camera is concerned, he's gone. But because we have dense sensors, we know he's still there. In fact, somebody crosses his path, and then he comes back into view very slightly. And you'd have a really hard time trying to recognize that as Bill unless you knew. But the motion sensors, even though they can't see his ponytail or whatever, they know it's him because they didn't see him leave. They knew he was there. And so they got him. There he is. And he talks for a while. And then, let's see, let's keep going. We have to ask the system to sort of keep going. OK. So let's see if I can do this right. OK. Zoom out. So he heads away from this area. And then he ends up, I believe, here. And we lose him again. I say, look into the future. And I think, there he is going back. OK, so now that I've got it in the computer, let me play it and show it to you. So we've got this whole interaction. It starts at 10:51. And it ends at 10:52. That can't be right. Oh, OK. Starts at 10:46, ends at 10:50 something. So it's a big chunk of time. And basically, we get all the video evidence. So what he does is he leaves his office. He goes to talk to one of the administrators for a while, for a few minutes. And then he disappears into this horrible ambiguity, which is the kitchen, right? And it's a horrible ambiguity because there's many people come and go from there. But if he goes to the kitchen, he has to leave the kitchen at some point. And it just so happened that in this case, it was relatively easy for me to find that leaving. And we don't know it's him except that that track goes back to his office. We have some reason to believe it's him. And then he walks in front of a camera. So there he is. That's the video evidence that, in fact, we got him. So this is his entire like coffee break, basically. So he comes out of here and goes up and gets coffee and goes back. So that seems like that's pushing the boundary pretty high, right? Like we can make these stories with just a few cameras and a bunch of sensors. We can make these stories that have pretty detailed descriptions of what people do during the day. So that's an indication that this boundary is pretty high. On the other hand, we don't know that he did anything embarrassing while he was walking down the hallway. So that pushes the boundary down. So that's this trade-off. That's sort of that's the scary demo. So.
Okay, for those of you who can join us for lunch, please feel welcome, and let's give a final thanks to our speaker.
Thank you.